with class 3. So we've covered Mohr Circle. We combined some stresses earlier in class 3, and we reviewed Mohr Circle, did a bunch of examples. Now I want to introduce or really kind of give an overview of the two basic kinds of problems that you'll see in this class mostly. One is what I refer to as the door handle problem. Okay, so by that I really mean a cantilever beam. So if you look in the problems section of Shigley, you'll see these problems in, well, let's see, in chapter 3 to begin with. But then if you go to chapter 4, you'll see some of these problems. You go to chapter 5, you'll see problems that look like this. You go to chapter 6, you'll see some problems like this. So that's like, you can just think of this, just to simplify things and to organize things. You have door handle problems, similar to that first example that I had, right? The thing that I refer to as this door handle, right? And what we're really trying to just have a generalization of problems that you might run across. And quite often one of the loading conditions you'll have is something that's cantilevered, or you might have something that is some kind of odd combination of some mechanism, some part that's going to be attached to a gas turbine, or some linkage, maybe even something, parts on an engine and that kind of thing. And you want to analyze it, and you look at the way that it's constrained, and you can see that it's cantilevered. You can kind of think of that's the type of category of the thing that you might kind of focus in on. The kind of techniques that you would use would be similar to something here of the simple quote-unquote door handle, which I'm kind of making fun of. The other kind of problem that we inevitably see, if you look into the back of Shigley, if you look into the problems, you'll see that we have simply supported shafts, right? And it can be part of a machine of some sort, right? Well, we're mechanical engineers, so we deal with machines quite often, and a shaft that's holding a gear or pulleys is very common. And so you've seen that I made a 3D printed demonstration little gear unit right here. So we could have, we might want to analyze this shaft, right? We want to design it and find all the stresses on it, or go backwards and decide what the diameters are if we're going to design it. Same for this. Quite often it'll be a shaft like this intermediate shaft that has 2 gears on it, so its loadings are just a little bit more complicated. Right, so that's where I want to talk about that in the remainder of class 3, and take a look at problems. Okay, so now Shigley has with the example in the book, example 3.9, they kind of I depart a little bit from the approach that they're showing in general problems. So I want to walk through this example, and maybe I will open up and show you what they're showing and show you what I want you to do instead. Okay, so let me see. I will open up Shigley here and have a PDF of it right here. Here's the 10th edition. I acquired somehow. Let's see. Will it open up? There you go. Open up Shigley. Kaboom. All right. So as I mentioned, if we go to, let's take a look at the problems in chapter 3, and so you could see some of them. So the problems of chapter 3 here. If we walk through them. So here you go. Here's some of the beginning of the door handles. Let's see. There's another. Okay, so this is a shaft. Yeah, that's a shaft problem. Shaft problem. Shaft problem. Shaft problem. Shaft problem. Another shaft problem. Door handle, and so you get the idea, right? So we'll also see some curved beams and things like that. We'll see later. But let's see the example that you will find for a basic shaft system here. Let's see. I said it was actually example 3.9. All right, so there's 3.3. looking through here, torsion. Okay, so here's the door handle example, example 3.8. That they're going through. What I don't like in this example is that they're not doing the 3 views like I have. I think it's much more difficult to visualize what's taking place in this isometric type of approach when you're looking at free body diagrams. Okay, so here's example 3.9. Here's where how Shigley approaches this right here. So I'll maximize this here. I might make it a little bigger. Here we go. And okay, so they're describing their approach. Okay, so right here is what I don't like. I don't like the fact that they're doing free body diagram, which is what this is representing right there, with these loads placed onto them, right? So I'm going to show you the way that I prefer to do it instead. But when working through this, it's also good to, know the way that Shigley is approaching it and read these carefully and walk through it so you can really understand it. Okay. So here is also they don't do the shear diagram here. They just do a moment diagram. All right. So here's actually the free body diagram that we'll be doing in 2 different views. So this is similar to what we're doing. And then they also show what the moment diagram are going to be. And we find where the maximum moment is located onto this as a combined, and that's what they're doing right here. And we're going to do that same thing. So there is a lot of similarities where I'm not doing completely different, but I'm going to go through a routine that we're going to repeat over and over again, is what I'm trying to tell you. All right, so I'm going to walk through this example, doing it my way, and then I'm going to do a separate example so that you can see how I want you to approach the thing, right? But anyway, make sure you check this out. But our mission in this problem is to find the we want to find. Let's see. We find the location and magnitude of the largest principal stress, right? So that's our mission, should we choose to accept it. So here's the original problem, and what's often not done in a lot of problems, by the way, is we might not, if these are pulleys, right? We might not give you like these loads. We might tell you that this one is like the larger of the 2 tensions is this much larger than the lighter, or more often they'll say that the looser side is 15% of the tighter side, or 20% of the tighter side. And what you just need to do is do a free body diagram to establish by looking down the end of this and just writing the sum of the moments, and you'll be able to find what the missing information is. So that's a very common type of problem. In fact, I can kind of show you where a problem like that is in Shigley. So maybe I'll do that. Need to focus a little more here. All right. So like you might see in one of these pulley problems, yeah, like right here, right? So, all right, so these right here, see, they show you tension 2 and tension 1, and they'll say that assume the belt tension of the loose side is 15% of the tight side. And then all you need to do is substitute like T for one of them and 0.15 T for the other, and then do the sum of the moments when looking down the end of the shaft. Or you might have the same thing here, right? So you'll see that these are missing information on these pulley ones, but they're not terribly difficult. So I'll make sure that we do an example where we cover that. But here is the example, just walking through. I already have it written out, so we'll work out the problem, the second example, and fully. But here's just a walkthrough. I've rewritten out this example, but doing it in the way that I would prefer that you do it. All right, so I want you to do a shear moment diagram in 2 separate views, in the XY plane and the XZ plane, if X is the shaft axis, and I usually make it that way, right? So make sure that we can visualize what's taking place there. So we take a look at the XY plane, right? And we can see that we would see these downward forces on pulley C, represented here. And I went ahead and added them together, right, that 500 and the 100. But we don't see the forces on pulley B because they're coming out at us. So we have a support in at A, and actually I usually write A-R-A-Y, so this would be ray, and this would be R subscript D-Y for this. But those are the supports at these bearings in the Y direction, right? And then I do I solve for the reactions right here, and then I get a shear diagram, and then I make a moment diagram onto this, right? And then I do it again here for the XZ plane, right? So we're looking down at that plane, the XZ plane. Okay, so now you notice that Z, because we're looking down on it, actually goes downwards, right? And we now we're going to be looking down upon this, and we can see that 200 and 1,000, so they combine to 1,200 here. And then we can't see the loads that are on C. And I'd like you to make a nice, neat sketch. Make it to scale if you can. And okay, so we solve for AZ, which I will also often call RAZ. I like to have capital R as showing reactions. And then capital RDZ, what I'll actually put here most of the time. And solve for these reactions, and then you can find the shear diagram from them, and then you can get the moment diagram. And what we want to do is find the moments at each of these spots. And here's the critical thing. We want to combine them, but make sure we don't combine that one and that one. They're in two different locations. But this and this are at the same location. They're just, one is looking at one part of the thing, right? One's, let's take these off right here. One is looking at like right here, and the other's looking at like right there, right? So they're 90 degrees off from each other. So we're finding there's a bending. It's bending this way and it's bending that way. I don't want to break this shaft. It's kind of delicate. It's hard plastic, but it's bending this way and then it's bending that way. So it's I don't have unfortunately I don't have my pool noodle with me, which is an excellent way to demonstrate this because it's flexible right here. So I don't have, I'm looking around for maybe one of those long erasers, right? One of those things. But anyway, in any case, I'll try to use this, right? It's like bending this way and it's bending that way, right? 90 degrees from each other. So it's actually kind of bending in a diagonal fashion, right? So in order to find the actual moment of the thing, we want to combine the moment that's here's bending in one plane with the bending that's in the other plane. And we do that just like we would do any vector. We find the square root of the sum of the squares. So we take that squared plus that squared, and we take the square root of it. And now we find the magnitude of the overall bending, because the shaft doesn't know one plane from another. It just feels that it's getting bent. And so it wants to find out what that maximum moment is. So we combine them like vectors and find the magnitude. Same thing for this point right here over at C, like right underneath the gear. Right, or right underneath, I guess it's a pulley in this case. We'd have like the bending is, like it's going to be going in this plane, and then we rotate it, and we find the bending in this plane, but we want to get the magnitude of it. So we have this 4,000 here and 4,000 there, and they combine for 5,657. So you see that the total, the larger of the two is happening at B. So that's one of the first things we could say, that bending stress is probably going to be the largest stress this thing is, chances are. But we have to calculate it to decide. But we know that the moment is largest right there. Now we also want the torque on this, and in order to find the torque, or as we mentioned before, we need to cut the shaft apart and then look inside the shaft to see what the torque is being in here. So I do a free body diagram of only this portion, and I do that right here. And you can see I've represented the torque by having this little arrow right here, and here's T for torque. And I prefer to use T for torque and not for tension, like you'll see in the book. I hate that. We have 1,200. You can see we do the sum of the moments about that axis, and we're able to find here is what the torque. And then also, by the way, if we were to do this guy by itself, right, there would also be seeing the torque inside, and it would also equal to 1,600. So you could do it either one. But a lot of times it's easier just to pick the one that you would be viewing from if you're taking your big eye and looking from that direction, right? So now we have the maximum moment, and we have what the torque is inside the shaft. Remember, we're breaking the thing apart, and we're looking inside and seeing what the two these loads are. Now, there's no axial taking place here, right? We can come up with a scenarios where a 3D shaft will have axial. For instance, if it has helical gears, there's actually a reaction. It's really not a lot compared to the other loads, but it could be significant. Depends on the application. There's other things we'll discuss where we might have an axial load, but there's no axial load on this. And they also told us to ignore transverse shear. I told you to ignore transverse shear. I'll often do that. We might do a problem where we show you how much the transverse shear is. Now, that's a little bit different from this example in Shigley. I believe they go ahead and do this. All right, so I wish I had kept this on to example 3.9. Now we got to search for it and wasting your precious time by doing that. Right there you go. Okay, so in order to find the transverse shear, right, we need to actually find the plane in which we are finding that maximum moment. You'll see here's the maximum moment. So in order to get the correct transverse shear, what we need to do is do the little vector approach here and find what plane, and you'll see that here's the plane that you have to be in, and then you're able to find what angle you're going to have that plane in, and then you'll be able to find what the transverse shear is going to be. But I believe, yeah, they ignored it in this case. Did they even say that in the problem statement? Bending and torsional stresses only, right? They're saying ignore transverse shear, basically. We do that a lot. But I will have several problems where we would do, oh, look, I had it right here already. Okay, so anyway, we get the geometry parameters. We don't need area because we don't have transverse shear or axial normal. And so we get I and we get J. And by the way, we could just multiply I by 2 to get J if we want to. And we find the bending stress, MC over I, right? And you get a 24,888. And then you get the torsional shear stress, right? You can see that it's only 2,414, right? TR over J. That's pretty small compared to this, right? So the bending is definitely the largest stress that's taking place. So what we want to do is we want to summarize this on a stress element, right? And then go to our Mohr circle. And we plot out the 2 points. Noteworthy that this is uniaxial stress, which means it's only in one axis, right? There is shear, but there's only tension on one side. We can also do compression, by the way. It won't change things. It'll just actually just flip this over to the other side. But a lot of times we'll just stick with the tension side. If there's a tension side and a compression side, a lot of times we'll stick with the tension side unless there's axial, that for whatever reason, maybe there's compression axial and there's bending. Then you want to go to the compression side of bending and add the compression axial to it, because that'll be the largest magnitude that you're going to find of stresses, right? So just be aware that you might do that. But a lot of times if there's both tension and compression, we'll just pick the tension side to do. So if we plot one of these faces, it's going to be that point right there. If we plot this face, it's going to land on the y-axis. Right, so that is a very common thing to happen when we have uniaxial stress like that. Now I go through the process as I showed before, the Mohr circle. We find the center, and in that case, it's just 1/2 of this, right? And then we find the radius, which is, in this case, once again, so this is going to be the leg right here of this, and here's another leg of this radius right there, right? So that this is a common scenario that will happen, just because this, in this loading condition, we end up with uniaxial stress. We can't really even get stress. It's we'll find that there's limited scenarios in which we will have stress in that other direction. One of them we will come up with is pressure vessels. They will have stress in that other direction, but quite often we'll only have uniaxial stress. And so once we have this the center and this radius, we can get principal stress, and I should probably change that to A, like I said I was going to do, and we'll have B. Right, and we're going to see why we have that A and that B coming up shortly. So we have the larger of the two principal stresses is C plus R, add them together, and we get 25,119 psi. I would probably say that's 25.1 ksi. And go ahead and say tension, but it doesn't really matter. And then here we'll say C minus R, and we get 0.232 ksi compression. There you go. So that's the example that's in the book, right? So look through that one and then compare it to this. But now let's go over to a totally different example. All right, so this is, here's another one. So I'm going to walk all the way through this one right here. And I keep having my focus problems right here. Literally and figuratively. I don't know if that's figuratively. Okay, so we have find the location and value of the maximum principal stresses of the loaded 44 millimeter shaft shown. Ignore transverse shear stresses. Now these are gear problems, but by the way, most other gear problems I'm going to show you, actually this force will come in at an angle to the gear, and that's just trying to get closer and closer to reality, because there is quite often a radial component, just as the consequence of the way gear teeth are shaped, the shape of them. There's always a radial component that's going on here, but we just have a tangential component. So I've already done the section properties for you for this, and I did it. This is a metric problem because it's good to be able to do metric and English units, U.S. units. Onto this thing, but I've got them for you. We don't actually need the area of the thing, but it's a 44 millimeter diameter shaft right here. All right, so let's do two views of this, right? Like I like to put them side by side. Just got to be a little careful with the amount of space that I use up, and use a straight edge here. So we'll use, and they decided to go Y, Z, and X. All right, so I'm going to do the Y Z plane here, even though I don't like that. I kind of wish I had started a little bit lower, but I'll make the do with the thing. And then I'll also do the XY plane, which in this case is going to look like this right here. But it's okay, so here's a Y and here's X, and I'll represent the gears right here. Sort of like that. Kind of try to make the same diagram. Doesn't have to be perfect, but neatness will actually help you stay organized. Keep your thoughts organized, keep everything organized here. So it doesn't hurt anything. And it usually doesn't even slow you down all that much. To use a straight edge and make the thing look good. By the way, it's just it'll make you stand out apart from your sloppy coworkers if you make really neat stuff, even if you're not naturally, I don't think that's true about naturally neat, but I know that one of my children, not to pick on them, has decidedly bad handwriting, and it just doesn't look like very good. Okay, so we've drawn this thing out, and in the YZ plane, if we're looking at it in that direction, we're only going to see that 7.5 kilonewtons, right? So we're going to draw that down and label that on there, 7.5 kilonewtons, right? And while we're here, let's take a look down at the XY plane over here, and we're going to look down upon this thing. We would see that 5 kilonewtons, and it would be going that direction right there. By the way, they could have not given us this 7.5, and we would have been able to find it, right? We'll show that in a second. All right, so from this scenario here, we can figure out what the reactions are going to be. They're going to be right here in that direction. And in this one, they're going to be a reaction right there and a reaction right there at these bearings, which we're treating as if they are simply supported hinge points. And so I'm going to call this one RAZ. And this one is going to be RAX. This one I'm going to call RBY. Nope, Z. Sorry. Keep forgetting. They decided to use the other to flip the coordinate axes around. And this is RBX, right? I'm going to draw this stuff in here. Let's see. Hope I left myself enough room. I'm not sure if I did. I probably didn't. It's all right. We'll use more paper. Will be a good example. All right. So I'm going to put my shear diagram like right around there. I'll put my moment diagram right there. Let's see. And then I do my statics underneath it. All right. So I'm going to take the it's good to put the little dimensions in there. I try to make them kind of small. I'll just put them right next to it. I don't necessarily need to do the leader lines. It's just to help me so I don't have to look back and forth between the diagram there, which could lead to me, let's see, 250. Talking at the same time is kind of difficult on this. All right, so I want to start out by finding RBZ. So I'll take the sum of the moments about A, and technically this would be in the X equals 0. And I want to go, this is clockwise, so it's a negative 7.5, and it's 150 plus 350, which should be 500, right? 500 millimeters, right? And this RBZ is going counterclockwise, so I chose it correctly. And it's going to be an additional 250, so that's 750 equals 0. So RBZ. And maybe I won't waste your time and my time by reinventing this. Okay, yeah. So at RBZ, I find out that that's going to be 5 kilonewtons. 5 kilonewtons shows up in there. Sorry, I guess my thing wasn't on the page. All right, and then I do the sum of the forces in the z direction equals 0, where upwards is there. And so I say RAZ, let's see, back up in there so we can see that. RAZ, which is going upwards, minus 7.5 plus 5 equals 0, and we could see that RAZ is going to be equal to, I could do that in my head, 2.5 kilonewtons. Let's, since we're doing that, let's go ahead and do it for the other guy over here. So we'll take the sum of the moments, do it about A again, but this time it's going to be about the Z, right? And this guy is going counterclockwise, so he's going to be negative 5 times 150. And this is going clockwise, RBX, and it's going to be also going to be 750, right? That's the length of the thing, right? So RBX is going to be equal to 1 kilonewton. Sum of the forces in the x direction equals 0, and positive is downwards, according to this, right? We're showing it that way. And so we have RAX minus 5 plus 1 equals 0. And so we got our AX is equal to 4, right? So let's go up to our shear diagram, up onto here. And so we're going to go 2.5. So I'll go like, let's say that that's 2.5. And it's going to be the same all the way until it gets to that load. That should have been a straight line. Looks like it's sloping. And by the way, this is V. And we could even say that it's kilonewtons right there. And then 7.5, it drops down. So I'll even try to make this look like it's twice the height of that. And we get a -5 kilonewtons. And then this guy comes back up and it comes back to 0, right? Let's see. Will that focus? Yes, right? So you can see, here's my reaction right here. It's 5. That's great. So what we end up finding, and I didn't leave myself quite enough space, but we'll try to do it. We'll try to make do with it. Our moment diagram. We want to get this point, but we also want to get this point right there, right? So what this is, and this is the moment diagram, and let's make these Newton meters, right? We have, now these are kilonewtons and millimeters, so multiplying them by each other will get us Newton meters. We know that. We have 150 times 2.5 will give us the area of that right there, will give us what that point is, right? And if we do that, 2.5 times 150 gives me 375 Newton meters at that point. Now we could also go 2.5 times 500. 2.5 times 500 is going to be 1,250. Or we could go 250 times 5 and we'll get the same number. We should get the same number, right? So the area here should equal the area there in order for the moments to balance out. So we get this 1,250 is going to be the value right there. Doing the same thing for the shear diagram over on this side, we have 4, right? So there's 4 right here and going downwards. So that's 4. And then it's going to go up 5. So it's just going to be 1 right here, right? So it's going to be 1. See if I can get that to look like that. So it's just 1.000. So we get to this point right here, and we can see that this is coming downwards. Now remember, this is positive down that way, so this is a positive, and so I should probably make that negative. So anyway, this point right here onto the thing is going to be 4 times 150, which is 600, right? And this is, by the way, I forgot to write, this is V, which is kilonewtons, and this is M, which is Newton meters. And then nothing else happens here, so we have to go to this. Should take a look and see that 350 plus 250 is 600 times 1, so that also confirms right there. And I like to put these cross hatches in here. Right? So if we go this other direction right here, we have 250 and 1, so this right here should be 250. Right? Now we have all of our statics done. That's all the statics that's part of this problem. Now let's do the stresses. Well, we got it. Well, actually, there's a little bit more statics to go. We want the maximum moment at, let's see, I guess they're calling this A, and that's B. They didn't really call it here. So we're going to call this maybe 1 and 2, right? I don't know, just for lack of other things right there. I guess I could call it, maybe I could just give it a letter, right? We usually use letters right there. So we'll say that that's going to be C and D right there, right? So we'll find the maximum moment at C, right? It's going to be the square root of two things that are happening at C, right? It's going to be here and here, right? They're on two different views onto the thing, but it's 375 squared plus 600 squared, and that comes out to 707.5 Newton meters. And then we have M max D square root of 1250 and 250. Now that we already kind of know that's going to be the location, because this guy right here, he's larger than everybody combined, everybody there. So 1250 squared plus 250 squared, and that's going to equal 1275. So you can see that it's mostly due to this guy right there. Now let's find that's now we're done with the statics, right? Well, actually, almost. We also need to find the torque, right? So we need to cut this apart, and I'm going to do just this part right there. So I'll do the FBD of just that thing, and then here's going to be the shaft, and I'll draw a cross section of that of the shaft. And I'm not going to bother putting the reaction loads, but in an FBD you would see like reaction loads into there, but we're going to leave those out. And this is 5 kilonewtons, and that dimension right there is 75 millimeters. And if that torque's going clockwise, this torque has to be, and this the torsion that's inside, in between the two shafts, that thing has to be counterclockwise. So the sum of the moments about the y-axis, right, because remember, this is the y-axis, we're taking it down right there, is going to be equal to 0. And so you're going to see, and we're going to go counterclockwise as positive. So we have positive torque minus my 5 times my 75 equals 0. So the torque, and by the way, this is millimeters and these are kilonewtons, so we know we're going to get Newton meters. We end up with 375 Newton meters is the torque inside that shaft. Now we can find the stresses. We're finally done with the statics. We could find what the bending is going to be is MC over I. Right? So we're going to have 1275. The C is 1/2 the shaft diameter, which is 44 millimeters. So 0.022 in meters is the radius of the shaft. And I did provide I as this right here, 1.840 E minus 7. If I calculate that out, I'm going to go ahead and just in one step get rid of 1 million of them and just write the thing out, 152.4 megapascals, right? My calculator actually said probably, 1.524 E8, right? But I knew that I could just get rid of 6 of those 8, and so that I ended up with 152 megapascals. And then my tau, okay, so, and I could write down that these are bending, but I kind of know from the context here that they are. We have TR over J. The torque is 375. Once again, we have a radius of 0.022, 22 millimeters, and the J was 3.68 E minus 7. So we have 3.680 E minus 7, and we'll end up with 22.42 megapascals, right? So one thing that we should do, I don't have enough room here to do my Mohr Circle. I'll do it on a separate sheet of paper, but here's a good idea. Let's go ahead and just summarize this. I'm choosing it to be tension, and we could figure out the actual direction of this. It depends on the element that we're choosing. Let's see, the maximum is right here. So what we're really saying is just to this side of the gear, right? Or the pulley. Now we should, mention that we're taking a look at here, and it's in between the two pulleys, and that we've kind of pretended like it's down the center. It's in the center. We're pretending like there's no thickness to this, but what we're saying here, really, in essence, is that we have the bending was done from the center of the pulley, right? This is the moment. If we go slightly over to the side, the bending, it's going to be a little bit less, right? We would actually be over to this side because we want to be. Let's flip it over this way. It's going to be to that side of the thickness of the gear, but we're just going to go ahead and stick with what's in the center. But it is going to be to the side because it's the torque, right? So the torque is between the two either pulleys or gears, right? The torque is in the shaft that's in between these two, and so if we're going to say that to be true, and let's say it's this gear, and it's got a force coming down there, it's actually going to be down that face in that direction. Now, when it comes to this, when it comes to the shaft diagram, the 3D shaft, I'm not going to be a stickler for this because we're not combining the transverse shear here. If we were to combine the transverse shear, we definitely want to make sure that we had the directions correct onto this. All right, so, but anyway, this is the 22.42 megapascals. All right, so this is that next step. So to finalize the thing out, I can go ahead, even though I don't have graph paper, right? I don't necessarily have to do this with graph paper. I can go ahead and do the best I can by eyeballing the thing, right? So I have this about 150. This is about 20. So I'm going to say that maybe, let's say that this is 20, 40, 60, 80, 120, 140, and maybe I'll come out a little bit further right here, right? So it's going to be like, okay, here would be like 160. So it's going to be something like that right there. But here is 20, right? That's about the same distance as that right there. So here's where that mark would be, and here's where that mark would be. And so I'm going to have that right there. So somewhere in there, that's going to be my C, right? So I'm going to say my C, and it's going to be, what I've done right there is I plotted this face right there, and I've plotted this face right there, right? And the center of this is just going to be 1/2 of this, right? Because that's 0. So, normally I would take the average of the two normal stresses right there, but one of the normal stresses is 0. So 152.4 divided by 2, which comes out to 76.21 megapascals, right? And then the easiest one to do is this for the radius right there. So the radius, in this case, it isn't always, but this is one where that lands on that axis, is just going to be the square root of this length, which is the center, plus the tau right there, which is 22.42 squared, right? So what I end up with is 79.44 megapascals. And did I get rid of my... No, oh, there it is. Now, I can also do this by hand, by the way. But I can also do it with this, right? Whoop. So I didn't do a great job. That should have landed there. Let's just pretend it landed on there, okay? Don't tell anybody. There you go. So anyway, let's see. Here's going to be the sigma. We're going to call it A, sigma A. And right over here, look at that, sigma B. Now notice it's going to be very, very small value of my compression. All right, so here goes. C plus R is 76.21 plus 79.44. Sigma A is 155.7 megapascals tension. And then sigma B here is C minus R. So 76.21 minus 79.44, we get a negative number, right? It ends up being, didn't write it down. Did I not write that down? All right, well, it wants the largest principal stress anyway. So this is going to be the largest principal stress that we might find. And but if we were to find this other, go for the other one here as well, 76.21 and 79.44, you'll see that we get a negative 3.23. So we say 3.23 megapascals compression. And then if they had asked us for the maximum shear that would be taking place, that's going to be right above the center, right there. And that would be equal to the radius, right? That's equal to the radius, 79.4 megapascals, right there. But this right here, that was what was being asked for. So that's a complete problem. I went through the long way around for it, but you'll do this problem over and over again, just so you know. Just because I want you to make sure that you're able to master it and completely understand it. So there you go. There is the last problem in class 3. And now we're really kind of done with review. Oh boy, it was 46 minutes. God, that was really long. I need to be briefer during class, but not so fast as to not be digestible. Let's balance the two. I'll do a good job this time, I swear.